Hi, question number 2. Prove by mathematical induction that for all positive integers n, dn over dx to the n into x squared plus e to the x is equal to x squared plus 2nx plus n into n minus 1 e to the x. The question carries 6 marks. Now we're going to differentiate the right-hand side, but then again, before we do that, we're going to check the base case. Okay, for the base case, we can let x is equal to 1. If we do so, then we look at the left-hand side. So we're going to differentiate this is d to the 1 over dx into into x squared e to the x. So I can use product rule, and this is my u, this is my v. Okay, u v prime, so u is x squared, v prime is d dx e to the x plus v du. So v is e to the x, and then u prime is d dx times x squared. And again, we can just differentiate this, and we're going to get x squared over here. So this is e to the x plus, then we have e to the x times the derivative of x squared, which is then 2x e to the x. Now, e to the x is common, so I have x squared into x plus e to the x, well, I would say rather e to the x, sorry for that. So I have e to the x, which is common, and then inside I've got my x squared plus 2x. Now that's the left-hand side. When I look at the right-hand side, and when n is equal to 1, I'm going to get all of that over here. So that said, so we're going to get x squared plus 2 times n, which is 1, times x into n minus 1, so 1, so plus 1 times n minus 1 is 0, then all of that times e to the x. So basically we have then x squared plus 2x times e to the x. This is exactly the same as that. So we can see that the left-hand side is equal to the right-hand side. So if that's the case, then it's true for n is equal to 1. So now we're going to assume, so this was the base case. So what is our assumption? So we're going to assume true for n is equal to k. If we do so, then we're just going to have to substitute k into the equation. And let's do that. So then I have d to the n, so that means d to the k over dx to the k is x to the square e to the x is equal to x squared plus, so whatever we have n, it's going to be k, so kx, 2kx plus k into k minus 1, and all of that expression times e to the x. Okay, so now that's the assumption. So we're now going to try to prove for n is equal to k plus 1. So let's get some space over here. Right. Okay. So d to the k plus 1 over dx to the k plus 1 x squared e to the x, we are going to differentiate the assumption that we got in the second part here. So d dx into d to the k over dx to the k. Now, x squared e to the x. This was the assumption that this was true. Right, so what we're saying then, it is d to the x, d dx into, then I have x squared plus 2kx plus k into k minus 1, and then all of that e to the x. So again, I can use product rule because I'm taking the second derivative. So this is going to be my u, and this is going to be my v. And I'm going to be using the product rule. Okay, So let's try and differentiate this. And so d to the k plus 1 over dx to the k plus 1 into x square e to the x is equal to, so we know it should be then uv prime plus vu prime. So u is all of that, so I have then x squared plus 2kx plus k into k minus 1. Okay, all of that times d dx e to the x plus, then I have v, okay, vu prime and v is e to the x, and then d dx, and differentiating everything here. So I got then x squared plus 2kx plus k into k minus 1. All right, so now this is my u. So if I were to differentiate e to the x, I'm going to end up with e to the x. So I have then x squared plus 2kx plus k into k minus 1, right? And then all of that times e to the x, okay? Plus then e to the x, differentiating all of that inside, I'm going to get 2x because x squared, the derivative of that is 2x. Derivative of 2kx is 2k. And the derivative of this, here, this one here is a constant. So its derivative is going to be equal to 0. So we can add 0 and nothing. So that's just okay. You just don't need to put the 0 there. The e to the x looks like it's common. So e to the x, and then I have inside x squared. Okay, plus 2k and plus 2k. Okay, so plus 2k. Right, then is all right, plus 2k plus k. Oh, sorry, 2kx, because this is my u. That's not the derivative. So 2kx, 2kx, 2kx. All right. Plus then k square into, well, I can say then k square, k plus, I mean minus k. All right. So that should be okay. I can just leave it as it is. So plus k into k minus 1. So let's just leave it as it is. All right, and then plus the 2x. Okay, so plus the 2x here, plus the 2k over here. Right, so what I have is then e to the x into x squared. So I want to simplify something, 2kx and 2x. So 2x and 2kx. So that means the 2x can go outside and I have k plus 1 inside. All right, now got k squared minus k plus 2k. So that plus k squared minus k plus 2k. So then e to the x. All right, so we have then x squared plus 2x into k plus 1. And over here, I've got k squared plus k. Simplifying further, this is going to lead to x squared, okay, plus 2x into k plus 1. All right, so plus k into k plus 1. Now, this is exactly the same as the given expression, okay, at the beginning. Because in the beginning, we had the right-hand side was given as x squared plus 2nx. You can see that n here is equal to k plus 1. So for n is equal to k plus 1, then I've got plus, you have n into n minus 1. N into n minus 1 times, and all of that times e to the x. Now what is n into n minus 1? So n into n minus 1 is exactly the same. Sorry about that. N into n minus 1 is exactly the same as k plus 1 into, okay, so k plus 1 minus 1, so which is then k plus 1 into, this one disappears into k. So this is the same as this. So we can see now that it checks out. So this is good. So what can we conclude there? So my conclusion is this, that if it's true for n plus 1, true. Okay, I'm going to say since true for n is equal to 1 and true under assumption, okay, for n is equal to k, therefore also true for n is equal to k plus 1. Hence I can say by mathematical induction, so therefore it is, okay, so let's get some space here, it is true by mathematical induction, okay, for all positive integers n. So here we are. Take care.